Now, we are ready now to say what error control coding does to uncoded BPSK system. So, here you have an uncoded BPSK system, you have a bit, you convert it into a symbol, noise gets added, there is a decision device, you do a symbol to bit mapping A hat. Okay. So, the rate R is said to be 1 here, okay, 1 in the sense 1 bit per symbol. Okay. Every bit carries 1 bit, every symbol carries 1 bit of information. Okay. Every bit is converted into only 1 symbol, okay, 1 bit, 1 symbol. Okay. So, your rate is also 1, okay, and that is the uncoded BPSK. What happens in coded BPSK? You do not transmit 1 bit at a time, you collect k bits into a message M. Okay. So, this terminology of message we will use again and again. You collect k bits into a message M. Now, this k can be greater than 1, it usually is, and it can be quite high also. In typical systems today, people use k of 1000, 10,000, 500, 100, 200, numbers like that. Keep those kind of numbers in mind. Okay. Now, you will take this message M and you will encode it using some encoder into a code word C, okay, and this code word will be n bits in length, and this n will be greater than k. Okay. So, you will take say 100 bits and produce a 200 bit code word. Okay. So, now when you do that, your rate goes down, right, your 100 got converted into 200. So, the rate becomes k by n bits per symbol. Okay. So, if k is 100, n is 200, you have a rate 1 by 2. Okay. So, once you convert it into a code word, what happens after that is similar to the uncoded BPSK case. You do a bit to symbol mapper, okay, and you get n symbols. How does the bit to symbol mapper work? 0 goes to +1, 1 goes to -1. Okay. There is nothing different about the bit to symbol mapper than the uncoded BPSK case. Exactly same thing happens. You get a symbol vector now S, okay, and this goes through the AWGN channel, and you have a noise vector here, okay, and it will have n values of noise. Okay. They are all independent Gaussian, but still it will have n values of noise, and you will have n received values. Now, you have the task of building a decoder which will take these n received values and put out estimated code word, which is actually n bits. Okay. Now, why will you go to all this trouble? Okay. Why should you do all these things? Why should you do coding? Why can't you just do uncoded case? The reason is written here. Coding enables the same BER, the same bit error rate at a lower SNR. Okay. So, this is an important story to remember about coding. Why would you do coding? You have a certain BER versus SNR trade off, right. BER is Q of square root of SNR. If you do coding, you can get the same BER at a lower signal to noise ratio. Now, why would you want that? Because in your system, the signal power costs you something. If you think of a mobile phone, the signal you are transmitting costs you energy, and that energy comes from your battery is getting drained. If you use lesser energy, right, then you can use the battery energy for other things, like maybe playing games on your phone, I do not know, maybe other things you can do with that, or your phone's battery will last much longer. Okay. So, your signal power has to be reduced as much as possible, but you also want to achieve the same bit error rate. Okay. So, if you do coding, you get this benefit. Okay. Without going for a higher signal to noise ratio, you can get the same bit error rate, get bit error rate, lower bit error rates at the same SNR, or at the same BER can be achieved at a lower SNR. Okay. So, this is what is important. Okay. So, that is nice. Okay. You might say it is interesting. So, let me begin by describing this plot here. This plot here actually shows BER versus EB over N naught. Okay. Now, most of you are familiar with digital communication will know that SNR is not the correct metric in the presence of coding. You have to use something called EB over N naught. Now, what is this EB over N naught? Where does it come from? So, let me describe that briefly here. So, if you remember from the previous picture, the uncoded case had a rate of 1. Okay. Every symbol carried 1 bit of information. Now, once you do coding, every symbol is not carrying 1 bit of information, it is carrying less than 1 bit of information. Okay. So, uncoded and coded, the comparison is not fair, right, because if you spend so much energy in the uncoded case for a symbol, you are transmitting 1 bit, okay. But if you spend the same amount of energy in a coded case, you are not sending 1 bit, you are sending less than 1 bit, right. If you want to send k bits, you have to send n symbols, so you have to spend n times the symbol energy and you will be sending only k bits, okay. On the other hand, in the uncoded case, if you send n bits with n times es, you will be sending n information bits, okay. So, you have to equalize these two things, and that is what EB over N naught does, okay. So, let me describe that. So, signal EB is the signal energy per information bit, and it is defined as Es divided by R. How does that come? This is n times Es divided by k, okay. So, k information bits, k message bits gets converted into n information bits, n code word bits. You have k information bits or message bits, you convert them into n code word bits and you actually transmit them on the channel. So, the total energy you take up is n times Es, okay. So, EB is actually the energy per information bit. So, n times Es is the total energy consumed for k information bits. For k information bits, you consume an energy of n times Es. So, for one information bit, you consume an energy of n times Es divided by k, and that is EB, okay. So, the noise power remains the same, n naught by 2 is sigma squared, okay. So, SNR is Es by sigma squared, one can write it in terms of EB and n naught, okay. So, instead of Es, okay, so here what did I do? Es is R times EB, okay. So, I have put that here R times EB and sigma squared is n naught by 2, okay. And if you simplify, you see that SNR is 2 times R divided times EB over n naught, or another way to write this is EB over n naught is SNR divided by 2 times R, okay. This is the main result, okay. So, you have to divide by 2 times R and plot it versus and convert SNR into EB over n naught. You have to convert SNR into EB over n naught by dividing by 2 times rate, okay. So, in the BPSK case, we know SNR is 1 by sigma squared. So, for BPSK, maybe I should write that here. For BPSK, EB over n naught is 1 by 2 R sigma squared. So, you remember this formula, it is quite important, okay. BPSK EB over n naught is 1 by 2 R sigma squared. So, if your rate is 1, EB over n naught is 1 by 2 sigma squared. If your rate is a half, rate is 1 half, if you are taking n to be 2 times k, then your EB over n naught is 1 by sigma squared, okay. So, that is the formula for EB over n naught. Now, you can convert your BER versus SNR formula that you had into EB over n naught, you will get an additional factor of 2, okay, because for uncoded rate is 1, okay. So, your SNR is 2 times EB over n naught, and that is what you have here, okay. And you can make a plot, okay. You can make a plot of bit error rate, this is BER on the y axis versus EB over n naught in dB, okay. How do you convert EB over n naught to dB? You do the same thing, you take 1 by 2 R sigma squared and then you do 10 times log base 10, okay. So, maybe I should write that down here, this 10 times log base 10 of 1 by 2 R sigma squared, okay, whatever rate you have, okay. So, if you put rate equals 1, then it is uncoded, okay. So, for the uncoded case, we know what BER is with EB over n naught, right. So, it is Q of 1 by sigma and that will convert as square root of 2 EB over n naught, and you can make this plot, okay. So, I will urge all of you to write a small piece of MATLAB or Python or any code you like and generate this graph, okay. This graph is very important for any error control coding class. You should be able to generate this plot of BER versus EB over n naught, BER in the log scale. So, you can see this is log scale, and EB over n naught in dB scale and for uncoded BPSK. Remember uncoded BPSK, this plot is simply Q of square root of 2 EB over N naught. Okay, so it is an easy enough formula and you plot this. And one particular data point is 10.5 dB, which corresponds to a bit error rate of 10 power minus 6. Okay, so just remember this, keep this in mind, it is a good metric to remember. So, if you want a bit error rate of 10 power minus 6 with uncoded BPSK, you need an EB over N naught of 10 dB or so, 10.5 dB. Okay. So, that means roughly signal energy is 10 times the noise energy, right. A dB, 10 dB is the same as factor of 10. Okay. So, that is the conversion that you have here. Okay. Now, what will coding do? Okay. If you do coding, if you do a very good code, in fact, you can even achieve something like this. Okay. So, let us say R equals half, a very good code. Okay. What is this very good code? We will see later on in this class. The codes in the 5G standard are very good codes and they can give you a picture like this. Okay. So, what have you gained? Look at this point. So, you have gained roughly about 9.5 dB or so, okay, maybe even more, look at the calculation. Okay. So, instead of having a noise power which is, instead of having a signal power which is 10 times as much as the noise power, it is enough if you have a signal power which is just a little bit more than the noise power. Okay. Imagine the savings, right, your battery will last that much longer, things do not heat up that much, everything is wonderful in this scenario. So, this is essentially what we will see in this class. We will see how these very good codes in the 5G standard can be built, encoder can be built for them, a decoder can be built for them, and how you can achieve these kind of coding gains. Okay. So, our presentation will mostly be from an implementation point of view, how to implement these algorithms, but we will spend some time discussing about where these algorithms come from, or where these codes come from and all that, but most of our focus will be on having an implementation for the codes in the 5G standard and maybe even show these kind of graphs. Okay. Maybe generate a graph like this and show how this works. Okay. Thank you very much.